Good afternoon.
Good afternoon, sir.
Okay, I will start. And if you don't have any question from the previous sessions, I will start the next chapter.
Yes, sir. Sure.
This week, we will start the free vibration of single degree of freedom systems. And we try to cover first the free vibration of an undamped system, which there is no damping in the vibrating system. Second, we will have a review on the Rayleigh's energy method. And finally, we wrap up with the free vibrations of viscous damped system. So we start with the free vibration of an undamped system. A simple form of a vibrating system consists of a mass and a spring. The mass is considered M and the spring is considered with the stiffness K. And also we need to consider a degree of freedom for this system. Here you can see we assume that the degree of freedom is X and the positive direction is to the right, and it will measure from the equilibrium condition. So we can extract the equation of motion for this system using two different methods. As you know from the dynamics, MM366, you know that we can use the Newton's second law and we can extract the governing equation for this system. We will have 1 degree of freedom, so we can write the force equation in x direction. The force equation in x direction, if you plot the free body diagram for this system, we will have the force in this spring at this point here. Here we will have the force which is equal to K times by X, and X is the displacement from the equilibrium position. So in the X direction, the force equation is equal to minus Kx because let me first, dear friends. Okay, so this negative is due to the direction of the force. The force is in negative direction of X. And we also have the acceleration in the right hand side of the Newton's second law. We have mass times by the acceleration, and the acceleration here is x double dot, which x double dot is the second derivative of x with respect to time. So we can extract the governing equation for this system easily using the Newton's second law, which is mx double dot plus kx is equal to 0, and there is no external force. So this is a ordinary differential equations with non-homogeneous term, without any non-homogeneous term, sorry, and the equation is homogeneous. The second method that we can use is the energy method, that because this is a conservative system and there is no non-conservative component in this system, we can use the energy method. I mean, we need to obtain the kinetic energy T and the potential energy U. Here we have a spring, so the potential energy will include the potential energy stored in the spring, and it's equal to half kx squared, and the kinetic energy is equal to half mx dot squared, which x dot is the velocity of the mass, and this is considered as a particle. So the kinetic energy is equal to the half times by the mass times by the velocity squared. So we can substitute into this equation, which is the energy equation, and the derivative of the summation of the kinetic plus potential energy with respect to time must be equal to 0. So we can conclude this equation. The derivative of T, or the kinetic energy, is 2 times by half times by m times by x dot times by x double dot, and the derivative of U, or potential energy with respect to time, is 2 times by half times by k times by x times by x dot. So we can factor x dot and take it outside of the parentheses. So we will have x dot is equal to 0, or mx double dot plus kx is equal to 0, which the second term results in the equation of motion similar to the Newton's second law, and this is the equation of motion for this system. So we have the equation of motion for a single degree of freedom without damping is equal to mx double dot plus kx is equal to 0, because there is no external force. So in the right hand side of the equation we have 0 and there is no external force. One note which is related to the mathematics, and you may be needed to extract the derivative and calculate the derivatives, is the derivative of a function ft to the power of n is equal to n times by the derivative of ft with respect to time times by ft to the power of n minus 1. For example, here, when we calculate the derivative of half mx dot squared, which is the kinetic energy, we will have 2 times by half times by m, which is a constant coefficient, times by x dot, which is ft to the power of n minus 1, and x double dot, which is df to dt, similar to this equation. So for example, here another example, we have the derivative of x double dot squared with respect to time is equal to 2 times by x triple dot, which x triple dot in fact is df to dt, and x double dot, which x double dot is ft to the power of n minus 1, because here n is equal to 2 and there is no coefficients. So here we only have 2 times by x triple dot times by x double dot. The second example, here we have sine 2t cubed. This time n is equal to 3. So we will have 3 times by df to dt, which is the d of sine 2t with respect to time. And it's equal to 2 times by cosine 2t. And ft to the power of n minus 1, which is sine 2t to the power of 2, or squared. So these are two examples, and you can use this equation for calculation of the derivatives for a function which is a function of time and it has a power. So this is only a review for the mathematical equations. You can use it in vibration to your calculations. Okay, any questions so far? Is it clear? No question? Any questions so far? Is it clear? Is everything clear?
Yes, clear, sir. All good.
Okay. The second case in the single degree of freedom system is vibrating of a mass and a spring system in vertical position. Here in this case, we will have an initial deflection. As you can see, before starting to vibrate, we will have some initial deflection due to this mass M. Here, the mass m will cause some initial deflection, and it's equal to, if we consider its delta st, it's equal to mg divided by k. So according to the Newton's second law, again, we can extract the governing equation for this system. The summation of the force in x direction, which this time x is in vertical direction, it must be equal to the mass times by the acceleration. The summation of the force is equal to the mass times by the acceleration. Again, acceleration is equal to x double dot, the second derivative of x with respect to time. In x direction, we will have the force due to this spring, and also we have the weight. So we can write minus k times by the x subtotal, which x subtotal is the total displacement of the x, or total elongation of the x, of the spring, sorry, and it's equal to the x plus the initial deflection. The direction of the force due to this spring again will be in upward direction when the mass m is going down, so it has a negative sign. The direction of mg is in downward direction, so it will be positive, and it must be equal to the mass times by x double dot, which is the acceleration. Now we can substitute the x total by its value, which x total, as I told you, is equal to x plus delta st, and delta st is the initial deflection of the spring due to the weight, and it's equal to mg divided by k. So you can substitute x total by this term, x plus delta st, and also you need to substitute delta st by this term, mg divided by k. And if you simplify this equation, again, you can extract the same equation for the horizontal motion, and it's equal to mx double dot plus kx is equal to 0. So you can see the same equation will be extracted for this system with vertical motion, and we can conclude the equation for the vertical motion and horizontal motion will be the same. But we can conclude two important points from this system. The first one is that always the vibration of a system occurs about its own static equilibrium position. So when you want to calculate and when you want to extract the equation of motion, you need to write your, for example, Newton's second law about its equilibrium position. Or when you want to write the kinetic energy and potential energy, you need to calculate them about its equilibrium position. And the second case, when in a system which the mass cause some initial deflection in your springs, we can neglect the weights in the driving equations in Newton's second law, for example, of motion. And also we need to neglect the static equilibrium position. So here, in this case, it means when you want to extract the governing equation for this system, you can neglect this delta, okay, and you can write the governing equation about the equilibrium position, and also you need to neglect the weight in your Newton's second law. Of course, for this system, because this is a very simple system, it's clear that you can easily extract the governing equation. You can calculate delta and mg similar to previous slide and extract the governing equation. But sometimes it will be a complicated system. For example, in multi-degree of freedom system, or later you will see when we have a rigid body, sometimes it will be complicated to calculate delta and also consider the weight in your calculations and finally simplify this. So the best method is at the first step, you neglect the initial deflection and also you neglect the weight in your equations. So this is the equation of motion for a single degree of freedom system. And now we need to solve this equation. As you can see, this is a second order ODE. or second order differential equations with constant coefficients. This is M, which is a constant value, and K, which is the stiffness, and again is a constant value. There is no non-homogeneous term here. In the right hand side, you can see it's equal to 0. So this is a homogeneous equation from the order 2. We solved some equations like this in I think in the previous session in revision of ODEs. I solved an equation like this, and here again we use the same method to solve this equation. This equation, the total solution is equal to the homogeneous plus particular. The particular solution is equal to 0 because the non-homogeneous term is equal to 0. So only we need to calculate the homogeneous response. The characteristic equation for this ODE is equal to M times by alpha squared plus K is equal to 0. This is an algebraic equation from order 2. Easily you can solve it. Alpha 1 and alpha 2, which are equal to plus minus I square root of K divided by M, which this term is called omega n, or the natural frequency of the system. As I told you, the natural frequency in fact is the eigenvalue of your equation of motion. So here easily we calculated the natural frequency of this system, and it's equal to a square root of K divided by M. So alpha 1 and alpha 2 are equal to plus minus I times by the natural frequency, and X is equal to C1 cosine omega nt plus C2 sine omega nt. And how we can extract this response from these roots? You know from previous part in revision of ODE, when alpha 1 and alpha 2 are equal to a complex conjugate number, you know that X, or the response, is equal to the exponential of real part, which here real part is 0. So here in this term, we will have the exponential of 0, which is equal to 1. So we don't have any real part. Multiply by C1 times by cosine imaginary part times by T, which imaginary part is omega n, plus C2 times by sine, again the imaginary part, which is omega n times by T. So this is the xt, or the response of this system. And C1 and C2, these two constant coefficients will be obtained from the initial condition, similar to previous part. We can assume that initial condition for this system is x naught and v naught. X naught is the initial displacement, and v naught is the initial velocity. Okay, sometimes x naught or v naught, one of them can be 0, or both of them can be non-zero, and it depends on your initial condition. We assume this general form for your initial condition. Now we can use them. At t is equal to 0, it means that you should substitute t is equal to 0 in this equation for x. When t is equal to 0, this term, sine term, is equal to 0, and only we will have C1 times by cosine 0, which cosine 0 is equal to 1. So C1 is equal to x naught, as you can see, and C2 will be obtained from the first derivative of x with respect to time. So if you calculate the derivative of x with respect to time, it's equal to minus C1 times by omega n times by sine omega nt plus C2 times by omega n times by cosine omega nt. This time, if you substitute t is equal to 0, the first term, which includes C1, will be 0 because it's sine omega nt. So sine 0 is 0. And we will have C2 times by omega n times by cosine 0, which is 1, is equal to V naught. So C2 is equal to V naught divided by omega n. And these are substitute into the equation. And finally, we can extract xt in total in general form, which x naught and v naught, as I told you, are initial conditions. So this is the response for STOF system, and you can use this relation for your response in your system. From harmonic motion, you know that you can also write the xt in only sine or cosine form. In the sine form, we will have a sine omega n t. Again, omega n is the natural frequency, and it's equal to a square root of k divided by m. Or you can write a cosine omega n t minus phi, which phi is the angle phase, and a is the amplitude of your vibration, and a is equal to x naught squared plus v naught divided by omega n squared. X naught and v naught omega divided by omega n, these two are c1 and c2. If you remember in harmonic motion, when I explain, they are the coefficient of cosine and sine function in your main response. Here you can see this is the coefficient of cosine and this is the coefficient of sine. So we use these two coefficients to extract the angle phase and the amplitude. Here you can see a and theta is equal to tangent inverse of x naught omega n divided by v naught, and phi is the tangent inverse of v naught divided by x naught omega n. This is the equation that you can convert your response into the only form of sine or cosine function, but most of the time you can directly use the previous method, I mean the common procedure, to extract the xt, and you don't need to find in this form. Okay, with one example, here we have an undamped S2F system has a mass of 1 kilogram, so m is equal to 1, and a stiffness of 2 kilonewton per meter. Here, this is kilonewton. Pay attention to this one. When you want to substitute into your equation, it's equal to 2000 Newton per meter. I mean, it should be converted into Newton per meter, and the mass must be into kilogram form. Find the magnitude and the phase of the response of the system when the initial conditions are -3 millimeter and the initial velocity is 50 millimeter per second. So easily you can calculate the natural frequency, which is equal to a square root of k divided by m. As I told you, k is equal to 2 kilonewton per meter, so it must be 2000 Newton per meter, divided by the mass, which is 1, and this is the natural frequency of your system, 44.72 radian per second. So this is the omega n. You can substitute a and calculate the phi, which is the angle phase. A can be clearly substituted by using the x naught and v naught, and also omega n, which is calculated here. You can substitute and calculate a, but for phi, when you substitute the tangent inverse of v naught divided by x naught times by omega n, you will extract two different value for your angle, your phase angle. The first one is -20.43, and the second one is -20.43 plus 180, which this one is pi, in fact. So we will have two values for the phi. One can be a negative value and the second one is the positive value. But according to this term, when the tangent inverse of this term is equal to 50 divided by a negative value, here in the denominator of the tangent inverse, we will have a negative sign. You know that tangent, of course, this is only a trick that you can use. Tangent is equal to the sine divided by cosine. Yes, this is the general formula for the tangent. When the sine is positive and cosine is negative, here you can see the denominator is negative because the x naught has a negative sign. So cosine must be negative and sine must be positive. So here I will show you. In the first quarter here, the sine is positive and cosine is positive. In the second quarter, we have a positive sine and negative cosine. So your angle of phase must be located in the second quarter. If you refer to the previous slide here, this one will be located in the second quarter. So this is our angle of phase. And of course, you should convert it into radian. I mean, you should multiply by pi and divided by 180, which is equal to 2.78. And then you can substitute, and this is your xt, the response. The amplitude is 3.2, and the angle phase is 2.785. If you plot the response for this response, x1 is in the form of cosine and sine. I mean, you can substitute into the general form of your response, which is x naught times by here. Let me show you. This is the general form, xt in the cosine and sine function. X1 is using from this equation. I mean, x naught times by cosine omega nt, which omega n is calculated 44. V naught is the initial condition and x naught is initial condition as well. So we're using this equation. So x1, this term is x naught times by cosine omega nt, which omega is 44.72. And this is v naught divided by omega n times by sine. So this is the first form of your response. The second form, using the harmonic equation, harmonic motion, is x2, which is a times by cosine omega nt minus phi. If you plot x1 and x2 for a period of time, you can see that the response for both of them here, this is the x1 and the second one is x2. If you plot this, you can see the response is the same. So there is no difference between x1 and x2. Both of them are the same response, but in different form and in different combination of harmonics. Any question from this example and so far? Is everything clear? No question? Is everything clear so far? Okay. So for a rotating system, we have studied the translational motion of the systems so far, but now we can extract the same equation when we have rotational motion. I mean, here we will have, instead of mass, we will have J naught, which is the polar mass moment of inertia, and instead of K, we will have KT, which is the torsional stiffness of a spring. So we will have a torsional spring, and we will have a mass moment of inertia about a point O. And if you use the Newton's second law, you can extract the same equation of motion and with the same response. And also the solution is the same, because again, if you refer here, you can see this is the same equation. Instead of x, we will have theta, but if you solve this equation, the natural frequency again is equal to the square root of kt divided by j naught, and the solution will be the same exactly. This time, instead of x naught as a and v naught as our initial condition, we will have, for example, theta naught and omega naught, for example, the initial condition, and you can substitute and solve this equation. In terms of mathematics, this is exactly the same equation as the previous equation in translational motion, but here we will have rotational motion, so the solution procedure is the same. Okay, here we continue with another example. We want to find the equation of motion of a simple pendulum. As you can see, this is a simple pendulum with mass m, and length L, which is rotating about point O. Here, if you want to extract the equation of motion for this system from dynamics, you know that the best option is using the energy methods. I mean, you can write the kinetic energy and potential energy for this system. Here, there is no spring, but the motion is a oscillating motion. I mean, the motion of mass m is similar to the mass in a spring and mass system. It is a periodic motion with a specific period and a specific natural frequency. So similar to the mass spring and mass system, we can extract the equation of motion, but this time we use the energy methods. The kinetic energy for this system, as you know, the kinetic energy will be stored in the mass or in the rigid body with mass or mass moment of inertia. Here we only have one particle with mass m, so the kinetic energy will be stored in this mass m, and it's equal to half times by mass times by the velocity squared. The velocity for this mass, if we assume this is, you know, this is a single degree of freedom system, we use theta as the degree of freedoms. So the velocity, angular velocity for this system is theta dot, and the velocity of mass m from dynamic, you know that it's equal to L times by theta dot. You know, when some particle is rotating about a point, for example, here, assume here we have a pin connection, we have, sorry, when we have a particle, this is a particle, for example, with mass m, which is rotating about this point O with angular velocity omega, and this length is equal to r, you know that the velocity of mass m, which is called v is equal to r times by omega. Okay, so v is the linear velocity of mass m, and it's equal to the radius times by the angular velocity. Here, the linear velocity is equal to L theta dot, which theta dot, in fact, is the angular velocity, and it's in fact the same omega. And r is the radius, which here is equal to L. So the kinetic energy for this mass m is equal to half times by ml squared times by theta dot squared. And for the potential energy, as I told you, there is no spring in this system, and we only have the gravitational potential energy, and it's equal to mgh, which, if we assume that this is the datum level, it means at this level, the potential energy is equal to 0. So the potential energy of this mass at the location when it's in theta position, its potential energy is L times by 1 minus cosine theta upper than the datum level. So H is equal to L times by 1 minus cosine theta. Okay, so we can substitute here, and this is the potential energy. Now you can substitute into the relation for the potential and kinetic energy. The derivative of this term must be equal to 0 because the kinetic energy and potential energy summation is a constant value. This is a conservative system. The calculation for the potential energy and kinetic energy will result in the equation of motion. Here you can see the derivative of kinetic energy is equal to m is a constant value, L is a constant value, so half times by m times by L squared, in fact considered as a constant coefficient, but theta dot squared, it's not constant, and the derivative of this term with respect to time is 2 times by theta double dot times by theta dot. Similar to the previous slide, I show you how to calculate this type of derivatives. For this term, we will have m times by g times by L, which are constant, again, coefficients, times by 1 minus cosine theta. the derivative of 1 is 0. The derivative of minus cosine theta is equal to theta dot times by sine theta. So we can substitute and we can simplify. So this is the derivative of this equation. We can again factor the common parts, m in both terms. We have L in both terms and also the theta dot. So the term into the parentheses must be equal to 0, which is L theta double dot plus G sine theta. It's equal to 0. And for a small deformation, as I told you, because in this course we only deal with linear equations and sine theta is a nonlinear term, we can assume that theta is small. It means that the rotation will be occurred in a very small period of theta. So using the Taylor expansion, we can assume that sine theta is equal to theta. So in this equation, we will have L theta double dot plus G theta is equal to 0, which this is the equation of motion for this simple pendulum. And to calculate the natural frequency, similar, you can see this is similar to the equation of motion for a simple spring mass system. But this time instead of x, we will have theta. Instead of mass, we have the length. And instead of the stiffness, we will have g. So the natural frequency for this system is equal to the square root of g divided by L. As you can see, the natural frequency is independent to the mass, and it's only depends on the length of the pendulum, and g is a constant value. You know, g is 9.8 on the earth, so omega n is only depends on the length of the pendulum. So the first conclusion is the period of a pendulum does not depend on the mass of the ball and only depends on the length of pendulum. Here you can see 3 different pendulum with the same mass, but the natural frequency for the blue one is more than the brown one, and is more, the brown one is more than the black one. So you can see that by increasing the length, the natural frequency is decreased. And the second conclusion, which is very important again, and of course the same conclusion, but in the different manner, the frequency and period of the pendulum are independent of the initial angular displacement amplitude. I mean, here you can see for the blue one, the initial condition is more than the brown one, and also the brown one is more than the black one, but the natural frequency and the period for all of them are the same, because again, we should mention that the natural frequency is only depends on the length of the pendulum. Okay, any question? Is it clear? Okay. Okay, we need to continue for a compound pendulum, but or because this is a 40-minute session, it's our time has been almost finished. We can wrap up this session now, and again we continue with another session. So please, I will wrap up this session and continue with another session just now. So this is the first session. The second session we continue again with the same link. I mean, please join the meeting again with the same link. I will stop and again start another session. So I will wrap up this one and end this one, and please join again with the same link. Okay. Clear? Okay, so I will stop this one.